Hello, everybody. And first of all, thank you for this invitation. And I know it's late in the day for a lot of people. And I have decided to do a more technical talk than I normally would, especially this late in the day. But I promise you, I'm going to try and keep things palatable. And Donna is going to be monitoring the chat. So if I'm getting way out of there, let me know and I'll try and pull back on things. Okay, so the idea of this talk is we came up with a technique called R power that I will try and explain what it is. And we, just like any mathematical technique, it was, sort of done under some assumptions, and obviously not all the assumptions are practicable or feasible. So how can we relax some of the assumptions and see where we are? Okay. So let's see, I am here and I need to, okay. So it looks like there is a lot of topics that I'm going to talk about, but essentially, this is going to be an estimation procedure that we are going to be talking about. And the supplementary materials and references is only if I have time and only if people have energy. But generally, my topic will start with multiplicity, talk about what it is, and sort of introduce R power, and then go into the normal means problem and talk about an existing estimator, which is a Gene Estimator, and then go on to our estimator, which is the Audible Estimator, talk about some results, show why this method works theoretically, and then show this method practically and go from there. So let's go. Okay. I'm not even gonna try and explain what multiplicity is, but just because I know there might be people who have, who kind of know what is going on, but not totally. So what I'm gonna do is come up with a very ridiculous example and then kind of take that example all the way through so that people get an idea of multiplicity, even though it's a very exaggerated situation. So the idea of multiplicity is the fact that if you make multiple decisions simultaneously, then you increase your probability of a type 1 error or a false positive. Okay, so I'm going to start with this very unrealistic arrest example. So let's assume we have a situation where there's a big demonstration going on and 1,000, and there has been some property damage. Cops come in and they round up all the people that are in the area. So let's say there were 1,000 people, cops, pick up all 1,000 of them. Okay. However, in reality, let's say only 100 people actually took part in the demonstration. The other 900 were innocent bystanders. Okay. However, cops rounded all 1,000 of them, and they have no idea who was innocent and who was actually a participant in the property damage. Okay. So also, neither the cops nor anybody has any idea how many actually took part. So here I'm telling you that, there were 100 who actually took part, but nobody would really know that in real life. If somebody goes over, you pick up everybody and then, pick up 1,000 people but the question that you're trying to figure out at that point is, out of this 1,000 people, how many of them are guilty or how many of them actually participated in this demonstration and how many of them were innocent bystanders. Okay. So, the decisions are really, the cops have to make 1,000 decisions because each person will have to be decided guilty or not guilty. Okay. And if these decisions are not made well, and taking into account the fact that we are making so many simultaneous decisions, what would happen is the probability that we make false decisions, a false positive, which means somebody who's an innocent bystander gets put in prison, will go up. So that is the idea of multiplicity, making multiple decisions. And if we are not careful, what will happen with multiple decisions is that we increase the chance of making wrong decisions or false positives. Okay. The literature on multiplicity would probably be 5,000-page book, just even touching the tip of the iceberg. There are many, many, many topics on this, or many, many papers, and I'm not even going to go through all the, even the tip of the iceberg. The general idea of multiplicity, the biggest idea was done kind of the family-wise error rate, which was also called the Bonferroni FWER. So all it said was, let's say you keep your overall type 1 error to be 5%. Okay, so the Bonferroni method in this particular scenario would say, take your 0.05 and divide it by however many decisions you're taking, 1,000 in this case. Okay, so that means each individual decision would have to be taken at 0.05 divided by 1,000. So there are 4 zeros and a 5, which would make each individual decision very difficult to actually figure out. So we need a lot of evidence to figure out if individually somebody has participated in this demonstration. Okay, so this particular method, while it was, it makes sense, it's the easiest, most it's the most intuitive one. It is difficult because it makes decision making very difficult. So from then on, there have been many, many methods that have been sort of a bridge between the original one and then trying to figure out, how do I do a better job controlling for this multiplicity? So there were Holmes, Symes, then finally, Hochberg and Hommel. And then the method that has stuck quite a bit these days is the 1995 method by Benjamin and Hochberg, also called the false discovery rate. And then following false discovery rate, there are many, many, many more papers. Okay, and I'm not even going to, talk about that, because what we are going to do is take a different tack on multiplicity. Okay, so rather than try and kind of control multiplicity and then say, okay, these are your, quote unquote, significant decisions, what we wanted to do was kind of look and see what practitioners actually do and then, make some adjustments. So the idea of R power is fairly simple. Let's say we have a hypothesis, in this case, whatever, one-sided, two-sided, in our, ridiculous example case, somebody is guilty versus not guilty. Okay, so this is our hypothesis. And we have got to make, in our case, 1,000 of these decisions. And the idea of R power was that in general, what I saw people do, like especially I was working with a lot of people in genetics who were doing genome-wide association studies or microarrays or, fMRI data. What people generally did was they did the 1,000 hypotheses, found their test statistic or p-values, and then essentially looked at, the top 40 or the top 50 of the ones that that were significant. Okay, and so the question was, they weren't really interested in how many were quote unquote significant, but which ones are the top contenders. Okay, and that became the the background of the idea of R power. So also, most people who are doing this kind of analysis use software. Lemma in R, actually in Bioconductor, gives you what is called a top table. What is a top table? After you've done your hypothesis, it gives you the top ranked test statistics, so the top ranked units of your test. And that kind of made sense because, and the way you create your top table is you ask R to say, I want the top 10, or I want the top 20, or I want the top 50. And in a genetic setup, this made a lot of sense because a lot of times the practitioners would say, I only have time and money and, energy to really follow up on a limited number of them. Okay. So telling me I have, 200 of them possibly significant doesn't help me because I have only money to follow up 50 of them. Okay. So, so they were looking at the top 50, irrespective of the fact whether it was really significant or not significant, just looking at the top 50. So that's the idea that, that sort of stems from our idea of R power. So what we were saying is that go ahead, do your analysis, find your top table. You decide how many you can follow up on. Can you follow up on 10? Can you follow up on 20? Can you follow up on 50? You decide. Okay, and then what R power is, it tells you that the probability that the list you picked, that top R list that you picked, did indeed come from the alternative. So the top R list is reliable. So the idea of R power is really reliability of your list. Okay. So essentially, R power is the probability that all the elements of my chosen list did indeed come from the research hypothesis. Okay. So essentially, let's kind of set it up. So let's say, just like we have 1,000 hypotheses, out of which 900 of them are coming from the null, no change, no effect. 100 of them, let's say, came from the alternative. Okay, let's pick the R to be, whatever number. Let's say the researcher says, I want my R to be 20. Okay, in that case, what we do is we do the hypothesis, rank them, take the top 20, and then find the probability that this 20, all of them did indeed come from the alternative hypothesis, that they are not contaminated by anything coming from the null. So in some sense, it's a pretty stringent criteria. But the reason I kind of thought of this idea was that, I knew that most practitioners just kind of use the top table anyway. But when they were trying to publish papers, there's always the question, okay, what is the p-value? What is the significance? So it's like, okay, it's not a p-value or a significance, but it gives you at least a probabilistic reliability of the list. Okay. So one of the things we are looking at is, we got the hypothesis, we have, say, 1,000 hypotheses, out of which we know 100 of them came from the alternative, okay, and 900 of them came from the null. Okay, and most of the times this is the type of scenario, because when you're doing this large scale testing, most of them there is no signal. Very few of them have signal. So I'm just kind of coming up with the 900 of them have no signal. So what is R power? So to find R power, what we need to do is make sure that the largest element of the null set, the ones in the null hypothesis, is not bigger than the rth element of the alternate list. Okay, so it's basically, if the largest element is bigger than the rth element, then it's in the our list, and then the list is not completely reliable list. So that's the idea. So it's a very simple idea. So what we did was we saw, okay, I can find the order statistic distribution. Okay, and that's exactly what R power is based on. You look at the order statistics, the largest element of the null list, the MA minus Rth element of the other list, and you look at the probability, given these conditions, what is the probability that, you are going to have, this is not going to happen. So 1 minus this probability will give us R power. Okay. So mathematically, what R power turned out to be is, you're really looking at a probability between, two order statistics. We can find the distributions of both order statistics, and it is an under independence normal distribution, equal variance. It came out to be something that could be analytically determined, and we found the analytical formula for R power. If you look at the formula for R power, you will see that the integration is not difficult at all. It's just an integration between 0 and 1. It's a normal density multiplied by the beta density. So again, very, very doable. Okay, but what are the entries into R power? What do we need to know? We need to know R, how many, what is my size of my list? We need to know how many were in the null, and correspondingly, how many were in the alternative. And your effect size, how big of a difference is there between the nulls and your alternatives. So that's, the delta is a big thing. Okay, but if you've done any power analysis, it makes sense that we would have delta. We kind of know delta because we are like, okay, when we do power analysis, we always give power as a function of your effect size. Same idea here. So if you look at R power, what do we need? We said that we need to know the number of null hypotheses. Okay, we need to know the effect size. Okay, the other two, R is determined by me, and M is a number of hypotheses that is known already. So pretty much, and if you think of delta, we can give people under different delta, these are the different, our powers. This is how reliable your list is. So really the only thing that we really need to have a good handle on is M naught, or how many came from the null hypothesis. So that was kind of a piece that, we finished the paper, we got it published, but that was a little bit of thingy that we knew that to make this method practical, we would have to come up with a way of estimating M naught. Okay. So again, I'm just kind of go back to the, my example, where here M was 1,000 people, M naught was 900, it's not known. M1 is 100, which are the guilty people. Delta is kind of a measure of how guilty they are. So how much difference is there between their level of guilt between one group and the other? Okay. And let's say, from the making it, realistic, the police want to arrest 20 of these people and put them in jail. Okay. Why do they want to only arrest 20? Because the jail has space for 20 only right now, okay, for tonight. Okay. So what we want to make sure, so what does R power give us? R power gives us the probability that the 20 that you pick, all of them are coming from the guilty list. Okay. Can we have more? Can we have less? Sure. But what we are really looking for is the people that we have are all coming from the guilty list. Okay. So that's what R power is. Okay. So again, as I said, the only piece that was kind of a sort of a thorn on our side was we really didn't have a good handle on the estimation of M naught, or how many null hypotheses we have. Okay. I know that, if people have questions, please put it in chat. I think Donna will let me know, but in general, I'll just go on right now and maybe take questions at the end. Okay. So in estimating M naught, so it's now an estimation problem. We really need to kind of think about the structure of M naught. In the original paper, what we did, so our original paper was published, I think, in 2016. In that paper, what we did was we said, well, let's just look at all of the hypotheses, look at the, how many of them were rejected without any correction, and take that as the number of, M minus that as the number of hypotheses in the null, which, at best is a very, very naive approach. And so we knew that this is something we have to come back to. So when we started looking at the literature on, estimating M naught, we found that there was some literature on it, because, when you're calculating your FDR, your false discovery rate, this is something that you would need to look at as well. So we looked at the literature there and found that, some of the methods that came up with this, and this method is called the normal means problem. So this particular problem is called the normal means problem. And so one of the things we saw was a lot of the techniques that were out there seemed like, there were some consistency issues. There were some, issues of not being very, really a good estimator, being extremely dependent upon the distributions that you used. But there was one approach that we looked at. It seemed to have some credence, that there seemed to be, it was a consistent estimator, and that estimator was kind of using a Lebesgue-Stieltjes integral of the characteristic function. Okay, and this estimator we will call the Gene Estimator. The 2007 paper is by Gene and Kai, and the 2008 paper is by Gene, and they use this estimator. So this will be sort of our competitor right now. So, okay. So in terms of Gene and Kai, they kind of started with the characteristic function. Again, for a lot of you who are in stats, you have learned characteristic function way back when you were doing a math stat class. So what is the characteristic function? The characteristic function is the expected value of the exponential of your imaginary part it mu, where we are taking expectation with respect to t. So the thing with characteristic function is, it always exists, okay? And one of the things why this particular function was used is it's got some really interesting properties. That is, the characteristic function is bounded between 0 and 1 individually. And if you look at this, if you make mu become 0, if mu is 0, then what will happen? You're taking expected value of something which is 1, expected value exponential of something to the power 0 is just 1. So the contribution is 1. Okay, so when mu is 0 in the characteristic function, your contribution of the characteristic function is 1. Okay, what if mu is not 0? If mu is not 0, okay, what we can show is that when t goes to infinity and mu is not 0, the limit of the characteristic function goes to 0. Okay, so these were like really interesting properties, because in the normal means problem, we can take any problem, and subtract off the true mean. So we can always say we are testing mean equal to 0 versus mean not equal to 0, okay, or greater than 0. So we are, our mu, we can think of it as 0 or non-zero. So if you think about it, all the null hypotheses, when their means are 0, their contribution to the characteristic function will be 1. All the alternative hypotheses, as long as we are looking at it in the limit, the contribution is going to be 0. Okay, so this is the starting point that we used, that Gene and all used, and the characteristic function. So what we need to do essentially is to come up with a function that is very like this characteristic function, but we can estimate it using data. So we can estimate it empirically. So the empirical characteristic function was actually something that was in the literature from the 1940s. I think it was Kramer's idea of doing an empirical characteristic function. And if you look from the last slide to this, all the empirical characteristic function does is basically take the expectation and replace it by a sum. So 1 over m, so it's like the mean of it, actual taking the mean of it. And the empirical characteristic function has this kind of interesting property that we talked about, that if you take, all the ones that came from the null and all the hypotheses that came from the alternative, you take the sum of it, you get the total value of this characteristic function, the empirical characteristic function. Okay, and it also showed that using strong law of large numbers, this is unbiased and consistent. So we have an estimator for the characteristic function, which is the empirical characteristic function, which actually uses data. Okay. Now the problem is trying to come up with a function that we can actually estimate. So the Gene estimator that I talked about essentially uses the characteristic function, but then what it does, it basically uses a Fourier transform to calculate a function that really mimics and has all the properties of the characteristic functions. So once we use this function, put our data in, all the nulls will technically give us 1 contribution. All the alternatives, if we let t go to infinity in the limit, at least is going to give us 0 contribution. So the empirical characteristic function will give us an estimate of how many, or the proportion of null hypotheses that there are in the sample. Okay, so in our test. So now let's look at the Gene estimator. I know this is late in the day and it's a lot of formula, but again, I just want the formula are there to just kind of back up what I'm trying to say. But what I'm trying to say is all we needed to do really is come up, or all Gene needed to do was to come up with a function, okay, that had the properties of the characteristic function and could be estimated, using data. Okay, so Gene used the Fourier transform, and I've given you, so basically, if you look at from the actual characteristic function to the empirical version of it, so we take the psi, which is the actual characteristic function, and we replace it by kappa. Kappa is kind of our empirical, something that we can actually estimate. And the form of kappa that Gene and all came up with is given, it's basically a Fourier transform. The thing is, it doesn't look pretty, but if you look at it, it's just an integration between -1 and +1. So it's very doable, to find, you put the data in, integrate over the data space, and you will get an estimator. Okay, so that was something that felt very, very interesting and promising to us, because we could use the Gene Estimator and then put it in our R power and go from there. However, one of the things, okay, so what is the Gene Estimator? It's basically an averaging wavelet, okay? And so the fact that the Gene Estimator is a consistent estimator, is something that, Gene and all, of course, proved that, okay? And the last part of the equation is important. If you look here, basically what it's saying is that, the Gene Estimator, it will estimate your 1 minus pi naught. So how many are coming from the alternative under, all the regularity conditions. So this was a really good news for us. Okay. However, we tried to use this estimator, we realized that there were a few issues. And when I show you some of our simulation results, which I will show you after our estimator, then you will see. So one of the issues that we saw was that even though theoretically it's a consistent and has, doesn't have large variance, in practice, whenever we did this, it had a huge variance. Okay. Which kind of is difficult because we are going to use the Gene Estimator and plug it into our power. And then, so if this estimator has a lot of variance, our power is not going to be very reliable either. So that's where we started thinking, is there a better way to do it? The idea is great, but there are questions of bias, it is biased, but more than that, the consistency was something that was worrying us, especially the amount of variability. Okay. So we came up with, the Gene Estimator is based on the Fourier function. So this is based on the Laplace estimator. And one of my students, Audible, actually came up with the idea. He's very, very good with the measure theory piece, and said that, look, Fourier transformation only uses the real space. Maybe if we also include the imaginary space and use a Laplace function, then maybe we can sort of tame the extreme variability. Okay, and that's essentially what we did. Okay, so before we go on, we will define, instead of the empirical characteristic function, the empirical moment generating function. The empirical moment generating function is just basically, your moment generating function, but calculated for data. And the piece that is important here is this. So instead, this piece, when we saw in the characteristic function, it was IT, but instead of saying it's IT, we are saying it is a function of t, s of t. And what kind of function? It's a function which is a linear function, which has a real part and an imaginary part. Okay, so that was what we were trying to do. Said, okay, and given this, if we find an estimator in this realm, what we can say is that this is a generalization of the Gene Estimator, because the Gene Estimator becomes a special case when we say AT equal to AI equal to 0. So if there's no real part, we only use this becomes the characteristic function, but we want to use the whole ST, then that is our empirical moment generating function. But we call it the complex one because it actually looks at the complex plane as well. So the Audible estimator, essentially same deal. All we are trying to do is come up with an estimator now based on the Laplace transformation that will mimic essentially how the characteristic function works. That means it's bounded between 0 and 1. When mu is 0, the contribution is 1. When mu is 1, when mu is not 0, but we let t go to infinity, the contribution will be 0. So all we need to do is come up with something that is based on the bilateral Laplace transform and come up with this. So Audible, after a fair amount of work, came up with this technique, and we decided that we would call it by his name. And so we called it the Adapted Empirical Bilateral Laplace Oracle. Okay, so Audible. Okay, I know it should be Audible because there is Laplace in there, but we thought it would be cute to just name it after him. So this is our, so the Audible estimator is essentially just, you know, a different way of calculating the kappa from the way Jin and Kai did it. Okay, so this is our kappa. Again, doesn't look pretty, and this is a slightly different, harder integration because there are 2 integrations that we need to do, but doable. Okay, so one of the things, and I think I spoke ahead already, so some of the key properties of this is that, you know, this particular function that we came up with, and Audible tried various functions. I mean, there were others that gave promise, but this one was the one, you know, he proposed, and we thought this was the best idea among all the other ones because it was, you know, it had all the properties that we needed. It was bounded between 0 and 1. You know, when mu was 0, it gave us a contribution of 1. When it was infinity, it gave us the contribution of 0. And the expected value of kappa, which is our oracle, our estimate for the function psi, is in, so it's unbiased. So that was another really good thing. So I am going to say ahead of time that the next few slides look awful because there's a lot of things in there. I'm just going to go and tell you the bottom line in these. Okay, I know it's late in the day to have this formula. The main thing that we showed here, and just because it's, you know, using the complex plane, it makes the method pretty complex. But essentially, one of the things we are showing in this, our second theorem, is that with this Laplace transformation, we can reduce the stochastic fluctuations, because that was a problem with our Gene estimate. There was a lot of fluctuations. So we control these fluctuations. Okay. Rest of it, don't worry about it. Okay. Theorem 3 is an important theorem because we showed that our estimator is indeed a consistent estimator for the proportion of nulls. So, you know, in this estimator, you know, went to the difference went to 0 if probability 1. So it's a consistent estimator. And again, you know, this was something, you know, we use some of the techniques Gene and all use, but in our scenario. And finally, this is, I think, the most important contribution of our method, that is this, you know, our mean squared error, which is bias plus variance of this technique, is of order 1/m, which means that the variance of this method is very, very small. Okay, so that is what we really wanted in these kinds of estimators, is to have really small variance. Okay. So simulation results. If you look at here, the green estimator is the Audible estimator. The black is the true value. Okay. The blue is Gene estimator, and the red is our naive estimator. Okay. We knew that the naive didn't work very well, and it definitely underestimated, but you know, that was what we had used before. So if you look at Gene's estimator and Audible estimator, none of them are really unbiased. Okay. The Gene estimator slightly is, you know, underestimates the true null. The Audible estimator overestimates the true null. The overestimation, you know, logically makes sense, because let's think about it. I've got, say, 1,000 hypotheses, out of which, you know, 900 of them are from the null. So for all of those 900, my contribution is 1. Okay. But the 100 that we have, those are going to 0 in the limit. So by themselves, they might have a little bit of contribution, right? So the fact that we are going to overestimate it a little bit didn't surprise it. Okay. And the overestimation gets worse as, you know, the number of nulls gets bigger. But you can see it's, you know, it's really, really close in terms of what the estimate is. But again, where our estimates really come in is the variance. So the red is the variance of the naive. Okay. The blue is the variance of the Gene estimator, and the green is the variance of the Audible estimator. Okay. And the black line is your, you know, the value of your the true value. So you can see that the Audible estimator is the variance is a lot smaller than the variance of the Gene Estimator. Okay, so using the Laplace transform, we did manage to tame some of this, fluctuations that we had. Okay, same deal, and we can see that the fluctuations are there in the Gene Estimator. And the good thing about the Gene Estimator is the fluctuations do get better when you are getting bigger and bigger pi naught. And bigger pi naught is something that we would expect in real life, because we would see that most of the times the nulls there are more hypotheses with no signals than with signals. So, so it makes sense that, Gene Estimator does make sense, but the variability was a bit much for us, so if the true value was 0.90, we could easily get values around, 0.84, 0.85, whereas, Audible's estimator was like 0.9000 something. So it's always very close to the true mean. Okay. So what I'm going to do is kind of conclude this, and, if people have time and energy, we can talk about the dependence piece, but otherwise we can stop. Okay. So what were our findings? Our findings basically is that yes, Audible estimator overestimates, the Gene's estimator slightly underestimates, but Audible's technique, the variance is so much smaller, the mean square error is so much smaller that, in terms of comparing those two estimators, there is no question about it that the Audible's estimator has a slightly better performance, not a slightly better, a much better performance. However, we do have to point out that, the Audible estimator is a double integral, and we're integrating over the real plane. We are using the Laplace transform, which is not as easy to deal with as the Fourier transform, especially since the Fourier transform and the characteristic function kind of goes together. So yes, the computational complexities are higher in the Audible estimator. However, it is, the time that you take to do this, I mean, even though obviously the Audible estimator takes longer, it didn't seem like it was that long or that much longer. And I don't really, if people ask me how much longer, I don't really remember, but maybe Audible's in the, and Swarnita are in the audience and they can answer. So in general, I think what we have done is we have generalized a type of estimators, the class of estimators, using characteristic functions by, making the class bigger by using, the complex moment generating functions, and essentially taken the extreme fluctuations that were coming up with the Fourier transform and tamed it using the Laplace transform. Okay. Continuing work, we remember one of the assumptions we made in R power was that all of the 1000 hypotheses were independent. Okay. We know that that never works in real life. If you're working on genetics, if you're working in genome-wide association studies, the ones that are, on the same organ, and, there are always going to be groups of genes that work together. Okay, so saying every one of them is independent, we knew was, not the best, wasn't the correct assumption to make, but mathematically it made sense, and so we went with that. Okay. So what we are doing right now is the Audible estimator paper, we have already submitted this paper, but this one, the dependence. So what we're looking at is going from independence to dependence is a huge jump, because, independence, your variance covariance matrix is a nice structure. Basically you have the identity matrix. The moment you go into dependence, there could be so many structures. So we started with the simplest of structures, which is equicorrelated case, that yes, they are not independent, but all of them are equally correlated to each other. Is it practical? No. But we decided that it was kind of a small step in the direction of dependence. So we did that, and we have some results already for, this structure. then we thought, okay, why not we look at it as a block diagonal? Okay, instead of, equicorrelated can be a block diagonals. Within the blocks, they are equicorrelated. Across the blocks, they are correlated differently. So each block can have a different correlation. And the reason we did this is because there are some nice mathematical properties that works for block diagonal matrices. The other piece is that if you think of the block diagonal, if I make the block size big, if I make the block size equal to the number of hypotheses, then I have basically the equicorrelated case. If I make the block size small, small, small to the point where each block is 1 unit, then we have the unstructured correlation case. So we thought, let's start here, and we have gotten some pretty good results about the block diagonal structure. So this is kind of where we are continuing our work. Future work, this is kind of a pie in the sky idea of, we saw that Audible Estimator overestimates, Gene Estimator underestimates. Can we come up with a convex combination of these two estimators and hit it on the nose? But the overestimation and the underestimation are so small, in the context of the problem, maybe it doesn't matter. Mathematically, it might be an interesting problem. So we did get, our methods are efficient, but we can probably get more efficiency if we kind of go into the Laplace transform and, look at the tuning parameters and see if we can tweak it a little bit more. And then finally, we came up, my area is inference, but we came up with, an estimate. So, the next question, of course, is, can we do confidence intervals on it? Can you do tests on this estimate? Will we do it? I don't know. We're just, still kind of thinking about these things. Okay. Collaborators that I want to thank, Audible, James Sijuwade, who really is the brains and the brawn and all the real thinking behind and all the measure theory behind the Audible Estimator. For work on dependent structures, Sharnita Chakraborty, who is a PhD student, current PhD student. Audible just finished his PhD. And then my co-authors for the original paper were, original R-Power paper were Nicole Lazar and Alan Gens. So definite, very grateful to them when we did this, and very grateful to all my collaborators. Okay, so I'm going to stop here and essentially take questions. There is some supplementary material that I have in terms of some of our results on dependence, but I figured it might be late in the day and nobody wants to hear any more from me.
Thanks, Jan. I don't see any questions, but I do see that you have some of your collaborators here, so that's really nice.
Anything people want to ask me? Anything?
It was really a great presentation. Thanks so much for ending our first Around the World conference with such an excellent presentation.
Thank you. I hope I kept people awake and aware for the most part, and I know there was a lot of, I could have taken out some of the formula, but it's hard to show something is consistent without showing it's consistent, right?
Right. Oh, absolutely. No, it was perfect. It was a great way to end the conference.
Okay. I will stop share.
All right. Well, thank you very much, and wish everyone a great remainder of December. And we were talking earlier about all of the wonderful things that CWS has planned for 2022 and Jan's presidency. So check the website for upcoming events.
Okay. Thank you, everybody. Bye.
Thanks, everyone.